came here to control my output. It's not only duty cycle, it's also the transformer turn ratio. That's great. Now, if I repeat the same discussion using the current now, current of the switch again is I am at 0. You see, because I said at the beginning, the same waveform, increase, decrease. Vd over Lm T. We know that. We know that the relationship between flux, and we can use it, or we can use directly the waveform of the current. Now, I maximum occurred at time T on. So again, we substitute here by T on, we go to the current. At T off, the voltage, the switch, you see here T off, the switch is not connected to the input. Okay, it's not connected to the input. So the voltage here transfer to the primary. Okay, it will be minus V1 N1 over N2, the trend ratio by output. So IM will be maximum, because here maximum, as you can see here, going to down here, minus the drop. I got it by using straight line equation. Okay, which is equal to I diode. Okay, I diode is the same IM N1 over N2. Now I can rewrite the equation here, making I maximum as a subject, as you can see here. I got this formula, which is used to find the maximum current, magnetizing current. For the switch voltage, here, this switch, it needs to block the input voltage plus the voltage transfer to the primary when the switch is off, which is N1 over N2 VO. Or we can simplify to make it in this way: input voltage over 1 minus D. Now, sometimes what they do, they connect the two switches rather than one switch. Two switches in series, as you can see here, this one and this one. These are the diode, freewheeling diode. You know what we use them. Okay, why we use two switches work together, on and off together? Because we want to distribute the voltage across these two switches. Rather than one switch handle the full voltage, it will be two switches handle half the voltage. Or sometimes we can make the circuit in parallel, two circuits in parallel for two switches. Each one work alone. It means each switch work with its high frequency transformer for part of the time, and the second one for the other part of the time. This is increase the reliability. And in case we lose one circuit, the second will work. Now the other converter is the forward converter. Forward converter, as I mentioned, is buck converter. We improve it rather than we use inductance. We use high frequency transformer, as you can see here. Okay. Now this circuit, if we come to find the voltage, okay, V1, as you can see here, it is input voltage when the switch is on. When the switch is open circuit, okay, what will happen? The output voltage transfer to the input voltage, as you can see here. Now, if I write formula, I will say V of the inductance is equal at the beginning, equal VD times the trend ratio transferred to the primary, to the secondary, minus the output, Kirchhoff. And when it is, let me say, open circuit, then VL equal minus VL. When I equate these two formulae and simplify, I will find the relationship between output and input. It's not only D as a buck converter. Turn ratio came to be another player. Now this transformer, actually high frequency transformer, can be represented by 3 winding, as you can see here. What would happen, sometimes we use 3 winding rather than 2. This is the first winding and 1. This is the second winding, the primary, and this is the secondary, and this is the third winding connected with diode in the opposite direction. Now, how this circuit work? By the way, this inductance is magnetizing, as I explained. How this circuit work? When the switch is on, current will follow here, here, back to the supply. This is positive, this is positive, and this is positive. Okay? For this diode will be, let me say, open circuit because it's reverse bias. But this diode will conduct the current, and it will follow. When the open circuit here, the current from the inductance here will release across the N1, which make this point as a negative. If this is negative, the diode here will be conduct, and the energy in storage here will be released back to the supply. while here the negative here will make this open circuit, and so on. Now the waveforms, as we explained here, it's shown input voltage, and for the current, it's for the switch increase and decrease and zero and so on for the switch. For the inductance, as buck converter, increase decrease. Now it's worth mentioning that when the switch is off, when the switch here is off, now N1 and N here 3 are both together, the two currents will equal to I2. We know from principle N times I equal N times I for the primary and secondary for the normal transformer, but here because the third, let me say, winding N3 will be added here to N1. Now the switch, when switch is off, the current I1 will be equal to my I minus I magnetizing, because I explained it. The current, this is the inductance and this is N1. Okay, current here will rotate in the opposite direction, so it will be minus. And there is no current will follow in the I2. And I3 will be N1 over N3 times I magnetizing, because transfer to the third winding, and the third winding is conducting because the diode is on. Okay, and then we can write V1 to be minus N1 over N3 Vd, because rotate in the opposite direction. Now if we integrate V1 across Lm, it should be 0 at the end. The store and release energy is the same, so it will be for one period for inductance to be 0, and this will lead to find Tm with respect to Ts. Tm is magnetizing, let me say, time for magnetizing, N3 over N1 times D. And this could happen when D maximum, okay, at D maximum. So if I come to substitute Tm over Ts by 1 minus D, okay, as you can see here, and simplify, we find D maximum, the highest duty cycle, is 1 over 1 plus N3 to N1. What does this mean? This means this is a constraint for the circuit. We need to consider the highest maximum duty cycle is related to N3 to N1. We need to select them carefully, because you know it's preferable to have wide range of D. As example, if D change from 0.2 to 0.8 is good, from 0.4 to 0.6 is not good enough, because we reduce the range of control. Now also this circuit can be work in series and parallel. As you can see here, two switches are in series, or two circuits are in parallel for the same reason, distributing voltage in series and reliability increase in the parallel. Now for push-pull inverter, you can see here this is switch 1, switch 2, and we understand what's going on the primary. On the secondary, as you can see here, two diodes, diode 1 and 2. Diode 1, when it's conduct, because this is related to the solid point here, when it's conduct, current will follow here to the load back in this direction. Okay, in this direction. And let me change the color just 1 second. And when this diode is conduct, current will follow here in the same direction back to the supply. So it depends which switch will conduct. And when there is no conduction for the switches, what will happen? Okay, let me just clean the place so I can explain on it. Okay, what will happen? The two switches will conduct. Okay, so the current, the inductance here current, this inductance current will follow here until here. Part of it, half of it here and half of it here, and back direct. So half of the current will follow here and half of current will follow in the second diode. For that, you can see that the switch at the beginning I diode is full current, and then to go to the half. Well, the same thing apply for diode D2. Now when we come to find VL, the inductance current, is input current transferred to secondary minus output currents. Whom say this? Kirchhoff. And for off, input current, input voltage, inductance voltage equal to output voltage, but in the opposite direction, because now they are similar to the book, capacitor and resistance, LRC. So voltage here is the opposite of this voltage. And the current of the diodes is half the inductance current. Now we can use this discussion and to find the relationship between output and voltage. It's found to be also the N2 over N1 twice N2 over N1 for the push-pull. Okay, because each switch will work half of the time. For half a bridge, now I don't need to discuss this again, we discuss it, but we use here half a bridge, one leg. The same discussion apply here. The only difference here is rather than VD, it will be VD over 2. And this reflected on the output-input relationship. You see there is no 2, there is no double. For full bridge, you see here two legs, leg 1, leg 2. Now we will use VD, similar to push-pull here, as you can see here. And the ratio, turn ratio of half a bridge is double that for full bridge. The same thing could we say for the current, switching current, double for full bridge. Now sometimes they use current source converter. What happened is they added here inductance to store energy at the beginning. The two switches are on, okay, current will follow here, here and here, okay, back. So they store energy here. Okay, the two switches can be conduct together, but we cannot keep them both open at the same time. Okay, one of them should connect at the next time. At the next time when this switch, as example, connect, not only the energy coming from the supply, the energy storage here at the beginning will be released. For that, this will give higher voltage. Okay, greater than D, you see here, duty cycle become greater than 0.5. The constraint in the previous circuits is crossed now. Now, final point to be covered here is the high frequency transformer, the magnetizing properties or characteristics. First of all, you need to know that the temperature increase, okay, flux density reduced, okay. See, this is 25 with 100. The curve will be different, okay. Now, this is one. The second issue, the core losses. This is the flux density. Core losses increase. You see here different curve. You see the upper here for 200 kilohertz, lower than 100 kilohertz. The other one 50, 20, 1. So you reduce the frequency, you reduce the core losses. Now, how we calculate the core losses? Because this is another losses added to the circuit. You need to consider it, and it reflects on the total efficiency of the system. It is equal to switching frequency to rises to power A, delta B max rises to power B. A, B, K are constants related to the material used. Okay. Now delta B is the peak swing in the flux density around the average. Okay. And how we calculate this delta B? We can calculate it by this formula. Input voltage over 4 and 1, the primary air, which is the cross-sectional area of the core, and switching frequency. It's worth to mention that for forward converter, the unidirectional in general, delta B should be lower than half B maximum minus B minute. Okay, while for full bridge, it's supposed to be lower than B maximum. Now, in conclusion, based on the previous discussion, 3 points worth to be highlighted here. First point is the large value of maximum flux density B max, delta B max, okay, here, this is large. The small, the cross-sectional area, relationship is inverse proportionality. And the second issue, the switching frequency below 100K example is limited by B max, okay, and for forward converter topology, okay, one directional, okay, it's limited by BM minus BR. The information or specification required for the circuit to be designed need to be considered using the data sheet. One more issue here is you can see the flux density is positive only in one direction, while positive negative in bidirectional. In the first one, unidirectional. Here the data sheet for one material used for let me say, high frequency transformer, you will find A, B, and K, and you can select them in your design. Okay, I will stop here. Thank you very much. Have a nice day.